Hello, linear algebra student. This video is for chapter 2.3, part 2. Continue with characteristics of invertible matrix and the application of invertible matrix theorem, IMT. In the last video, we talked about how to prove this whole list of statements, and concluding them, they actually are connected to each other. And the connection seems to be through D and G. Namely, whether this equation has trivial solution or has at least one solution, and then that's how you connect with the transformation and also the linear independent sets. And that's actually the power of invertible matrix, or the power of the independent set and invertible matrix. That's how they connect together. So we're going to use those to look at matrix. In this particular example, look at matrix. If we can detect a matrix is invertible without actually using the calculator of converting them into REF and look at if it is can be converted to an identity matrix. So far, that's the only way to prove that something is invertible, right? So, before we go into doing that, one thing we should notice is we say a matrix is invertible if we can find another matrix such that the matrix with the other matrix would multiply into identities, and the multiplication can be left and right? So from the statement that we have, you can find C A equal to I or A times D equal to I, and both of these are the same A inverse. And if you can find the inverse, it must be unique also. So this is the uniqueness of inverse matrix. You can prove it by using the IMT also. The other things I should mention is this invertible matrix theorem also describes the property of singular matrix. That means if it is not invertible, then all of the other statements are not true, meaning they would not be independent columns. You will not have n-perfect position. So basically, these two things are not true if it is not invertible. So that is exactly what we're going to use. If someone gives us a matrix and we just want to know if it's invertible or not, or if there is a transformation based on a standard matrix like this, we want to know if we can if it's a onto is it onto if it's a if it's a one-to-one, then we can use the invertible things to prove it too. Okay, so let's look at if someone gives us a matrix, discuss if they are invertible. So that means we can look at whether it had n prefix column or independent column to conclude if they're invertible. So because we have two column vectors and they are not multiple with each other, whenever it is just two and they are not multiple of each other, we can say they must be independent, right? I've forgotten what section it is in chapter 1. So they are independent, and because they're independent, which is, I think, is condition E, and that would prove condition A, which makes it invertible. Condition G, yeah, they're linear independent. So whereas in B, we obviously can see that column 1 is 2 times of column 2, negative 2 times of column 2. So they are dependent. They are not independent, or so that that means A is not invertible. It's a singular matrix. Okay, so without doing RREF. And the third one, we would use the transpose, because if we do the transpose of this matrix, let's say this is A, then A transpose would become negative 4, 0, 0, 2, 1, 0, 3, 2, negative 2, which is a which is a row echelon form with 3 perfect position, Three superposition meaning it is it meets the condition for what was it? Superposition is C, right? C had three superpositions, so it must be. So it's for C. C imply A inverse itself, no, A transpose, not A inverse. A transpose is invertible. A transpose is invertible. This is A transpose, and it is satisfies C, so A transpose itself is invertible. And then because A transpose is invertible, so L would imply A, right? A transpose is invertible means A is invertible, so it is invertible. What about this one? This one has a zero column. Of course, it is dependent, right? So we say that anytime you have one zero column, they must be dependent because you can say zero or one times this column plus this. Yeah, so it's dependent columns. They are not independent, so it is not invertible. It's the opposite of the E. Not E, so not A. And what about this one? This one we don't have anything to help us. We have three columns, so we can look at just multiples. It's not a transpose, and it's not easily to see how many different positions. So we're just gonna do by hand, do a REF, okay, by hand. So it's very easy to do. Just do a negative 3 of R1 plus R3, right? Put it back into R3. So that would mean negative 3 times negative 4 is negative 12. Negative 3 times 2 is negative 6. And add to R3, which is 3, negative 6, 0. So that means 1, 4, 2, 0, 3, 1, and also 0, negative 18, negative 6. And you can obviously see R3 divided by negative 6. Put it back into R3 would become 1, 4, 2, 0, 3, 1, 0, 3, 1. And this 2, if you subtract or R2 times negative 1 plus R3, put into R3, you would have 1, 4, 2, 0, 3, 1, 0, 0, 0. Okay. So avoid doing the calculator. So this would be means it has only two perfect position, so it is not invertible. What about the next one? Wow, this one is really long. But we can still do the this one is actually quite hard, right? If you do it by hand, so let's try to do a RREF. I think this one, because it's not easy to do the. So I have it written here: negative 1, negative 3, 2, 5, negative 2, 4, 3, 2, 3, 1, 2, negative 1, 0, negative 4, 2, 1. So I do the reduced row echelon form is actually we have 4 perfect position. So it's row reduced to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, which is B. Right? B would go back to A, so it is invertible. Okay. One of the things that is important is the fact that if A is a invertible matrix, A transpose is an invertible matrix, and actually, as a side effect, you can see when we prove it, you can see that what is the inverse of A transpose of A transpose? The inverse of A transpose is A transpose inverse. Okay, it's A inverse transpose. It's A inverse transpose. So you can say A transpose inverse is actually A inverse transpose. That means these two are like that. This is actually how the way we prove it. You can show it. So in the class worksheet, I'll ask you actually do an example to investigate that. But we can also use IM2T, so you can do that. Further investigation of IMT is this true-false statement. So see if you know all the statement by heart. Okay, so let's say if n times n matrix D such that AD is I, that is also a matrix such that CA is I. So of course this is true, right? Always true, because I think that is what J and K or something. If you look at IMT, what was it? J and K. They're actually J and K, and they it's IMT's J and K. So they are imply each other. If the column, so it is always true. Always true. If the column of A are linear independent, then the column of A span Rn. Well, so this is the result of IMT also true, always true. Based on the onto, right? Maps Rn onto Rn. Linear transformation. Yes. Yeah, it's H and what? H and can't remember what it is. At least one solution. H and at least one solution is what? At least one solution G. H, yeah, there's a G and H. Yeah, G and H. Yeah. So it's G and H of IMT. The equation AX equal has at least one solution for HB, then the solution is unique for HB. Do we know that it is unique? It has only one solution, at least one solution. Well, we don't know if it is unique for AX equal to 0, but we can tell that it is unique for, so it is unique for AX equal to 0. We proved that, right? But we don't know if it is true for all the B, right? So this is sometimes true. Is it? This is unique for each B. If the linear transformation, because we'll look at that. At least one solution, if it's, well, they say it is 1-to-1, okay, and it spans it, it maps onto, right? It doesn't guarantee that it is a unique solution, though. Okay. Oh yeah, and also this doesn't guarantee that A is an N. Yeah, A may not be a N to N. They didn't say that A is a square matrix. So if it's a square matrix, I think it is. But if it's not, then you don't know, right? So it's not very clear here. Here, if the transformation at Tx equal to Ax maps Rn to Rn, so this is the N to N times N matrix, then A has N perfect position. So this may not be true because they just say that it maps it. So it doesn't mean that it is a 1-to-1 or anything. So it is sometimes true. So we're going to continue in the next video. Okay.